All right, welcome back to TalkTensors. Today we're diving deep into this paper. Looks pretty fascinating. GenHPE, Generative Counterfactuals for 3D Human Pose Estimation with Radio Frequency Signals. So I've a lot going on in that title, I think. This whole idea of using RF signals, radio waves, to essentially see how people are moving.
Yeah.
It's the really interesting area of research. And this paper, it seems like, it's taken a pretty big step forward in addressing some of the limitations of RF-based pose estimation.
Yeah, I think one of the biggest challenges in this field has been, you can train a model to work really well in one specific scenario. You get a bunch of people in a room, you set up your RF sensors, you collect a bunch of data, and you can train something that works amazingly well.
Yeah. Seems pretty straightforward.
But the problem is that it doesn't necessarily translate to other environments or other people. And that's what this paper really tries to tackle.
Yeah. And I think to maybe make that a little bit more concrete for listeners who aren't as familiar with this sort of stuff, it's kind of like, you have a language model that's been trained on one person's voice.
Yeah.
And then you expect it to understand somebody with a completely different accent in a really noisy room.
Right, exactly.
Like there are all these things that can get in the way and make it harder for the AI to figure out what's going on.
Yeah, and I think the core of this problem is what they refer to in this paper as these domain-specific confounders.
Okay, confounders, like what kinds of things?
So, I mean, it's the fact that each person is different, right?
Yeah.
So, like, the way RF signals bounce off of you is going to be different from the way they bounce off of me. And it's not just about our pose,
right,
like how we're standing or how we're moving, but it's also about, your size, your density, even your clothes can affect how RF signals interact with your body.
Right. Interesting.
And then on top of that, you also have environmental factors, right? So the room itself, the layout of the room, the materials on the walls, any electronic devices that are in the room that might be emitting their own signals. All of these things add these extra layers of complexity to the RF signals that the model is trying to learn from.
So it's like it's trying to see the pose, but it's also seeing all this other stuff. It's almost like noise that gets mixed in with the actual signal it's looking for.
Exactly.
Okay, so that makes sense. And you mentioned that this could really hurt performance.
Yeah.
Like how much worse does it get when you try and take a model trained in one scenario and apply it to another one?
I mean, it can be pretty significant. Yeah. And actually, this paper points out some numbers from previous research in this area. So, for example, there's one method called PyW3D, and when they tested it in a cross-subject scenario, meaning they trained it on some people and then tested it on different people, they saw an increase of like 24 millimeters in their MPJPE, which is like their mean per joint position error.
24.
Yeah. And then when they tested it in a cross-environment scenario where they trained it in one room and then tested it in a different room, they saw an even bigger jump, like 35 millimeters increase in their MPJPE.
Okay, so that's pretty significant. I mean, we're talking about centimeters of error, right?
Yeah.
Like that's not just a small little blip. That's a real problem.
Yeah.
If you're trying to use this in a real world application.
Right.
Okay, so it seems like this issue of generalization is like the big elephant in the room, or the big confounding factor in the room, I guess.
Confounder in the room, yeah.
When it comes to RF-based pose estimation. So how does this GenHPE approach, how does it try to address that?
Okay, so the key idea here is that they're using what they call generative counterfactuals. Mm-hmm. And essentially what they're doing is they're training generative models to learn the relationship between human pose and RF signals.
Generative models, so they're not just like a classifier or a regressor or something like that. Like these are models that are designed to actually create new data.
That's right, yeah. So they're learning the underlying distribution of the data so that they can generate new samples that look like the real thing.
Yeah.
And in this case, what they're doing is they're training these models on human skeleton labels. So, the 3D coordinates of different body parts and the corresponding RF signals. Oh. So the model is learning, okay, given this particular pose, what kind of RF signal would I expect to see?
Got it.
And this is where the counterfactual part comes in. So once they've trained this generative model, they can start to manipulate the input. Okay. So they can say, okay, what if this person didn't have an arm? What would the RF signal look like then?
Let's delete an arm and see what happens.
Yeah. Or what if they were missing a leg? And obviously you can't do this in the real world.
Right.
You can't just like remove someone's arm and see how the RF signals change, but you can do it in simulation.
Yeah, in the world of the model.
Yeah, exactly. And so by by creating these counterfactual scenarios where they're virtually removing body parts, they can start to isolate the effect that each body part has on the RF signal.
Right. So it's like they're saying, okay, we know what the signal looks like with the arm. We know what it looks like without the arm. Let's subtract those two and see what's left over. And whatever that difference is, that's what the arm is contributing to this whole signal.
Yeah, that's a great way to put it.
So it's like they're taking this complex signal and they're kind of teasing apart all the different components that are contributing to it.
Right. And the really clever thing is that by doing this, they can start to mitigate the effect of those domain-specific confounders that we were talking about earlier.
Okay, so how does that work?
Well, think about it like this. The things that are different between you and me, the way our bodies interact with RF signals, those things are going to be pretty consistent across all these different counterfactual scenarios. So if I remove your arm or I remove your leg, the way your body, like, the size of your body, the density of your tissue, those things are still going to be there.
It's just the arm that's gone, right?
Exactly.
Yeah.
And the same thing with the environment.
Yeah.
So the layout of the room, the materials, the walls, all that stuff, it's going to be the same whether you have an arm or not.
Okay. So the confounders are sort of constant throughout all these different counterfactuals.
Exactly. And so when you calculate the difference between the counterfactual signal and the original signal, those confounders essentially cancel out because they're present in both signals.
Oh, interesting. So it's like you're subtracting the background noise away.
Right, exactly.
Yeah.
And what you're left with is a signal that is more representative of just that specific body part that you removed and less influenced by the individual or the environment.
Okay, that's really clever. So they do this sort of virtual surgery. They remove each body part. They see how the signal changes. They get these kind of isolated signals for each body part. Then what do they do with all those signals?
So once they have these isolated signals for each body part, they aggregate them together to create what they call a domain-independent representation of the pose.
A domain-independent representation.
So basically, they're taking all these little pieces of information and they're putting them together in a way that is less sensitive to the specific domain that the data came from.
Okay.
And, the way they do this is actually fairly straightforward. They just concatenate all those different signals together.
Okay.
And then they apply a linear transformation, which is just, a fancy way of saying they're multiplying it by a matrix.
Got it.
And this gives them a new feature vector that represents the pose in this domain-independent way.
Okay, so now they have this new representation of the pose that sort of has all the noise stripped away from it.
Right, exactly.
What do they do with that? How does that actually help them do pose estimation?
Okay, so this is where the second part of their approach comes in. So they take this domain-independent representation and they use it to regularize the training of an encoder-decoder model.
Okay, an encoder-decoder. So this is kind of like a classic architecture in machine learning for dealing with sequential data or data that has some kind of structure to it.
Right, and it's a very common approach for pose estimation in general.
Got it, okay.
So the encoder takes the raw RF signals as input, and it learns to extract features from those signals.
Okay.
And the decoder then takes those features and uses them to predict the 3D pose.
Okay, that makes sense.
Oh.
So, but what's the role of that domain-independent representation that they created earlier? Like, how does that fit into this encoder-decoder framework?
Okay, so they use the domain-independent representation to basically guide the encoder to learn features that are more robust to domain shifts. So they add a regularization term to their loss function that encourages the encoder to produce features that are similar to the domain-independent representation.
Okay, so it's like they're saying, hey, encoders, don't just learn any old features that help you predict the pose in this specific data set, but learn features that are also consistent with this more abstract representation of the pose that we created earlier.
Right, yeah. They're essentially trying to force the encoder to learn features that are more general and less tied to the specifics of the training data.
Okay, that makes a lot of sense.
Yeah.
So they're basically using this domain-independent representation as a kind of a teacher or a supervisor to help the encoder learn the right kinds of features.
Exactly.
Okay, cool. So let's talk a little bit more about the specifics of the encoder and decoder that they used. Like, what kinds of architectures do they use?
So for the encoder, they use a relatively simple architecture. It's based on a UNet, which is a convolutional neural network that's commonly used for image segmentation.
UNet, okay.
but they've simplified it a bit to make it more suitable for RF signals. And then for the decoder, they use a two-stream architecture. So one stream processes the features from the encoder, and the other stream processes the skeleton embedding.
Okay, skeleton embedding, right? So this is that kind of higher level representation of the body that they created earlier.
Right, exactly. And then they combine the outputs from these two streams using self-attention, which is a mechanism that allows the model to selectively focus on different parts of the input.
The self-attention.
And finally, they output the predicted 3D pose.
Okay, so sounds like there's a lot of like pretty standard machine learning techniques being used here, but the real novelty is in that first stage where they're creating those domain-independent features.
Right. I think that's really the heart of their contribution.
Okay, cool. So they train this whole system. They've got this encoder-decoder with this special regularization term. Let's talk about the experiments. Like, how do they actually evaluate this approach?
So they evaluated their approach on 3 publicly available data sets.
Okay.
And these data sets represent different types of RF signals. So they have a Wi-Fi data set, a UWB dataset, which is ultra-wideband radar, and an LMM wave dataset, which is millimeter wave radar.
Okay, so they're really trying to cover a broad range of RF sensing modalities here.
Right, exactly, because they want to show that their approach is general and it can work across different types of RF signals.
Got it. So Wi-Fi, WB, MM wave, what kinds of, like, just to give people a sense of what these signals are actually like, can you describe those a little bit more?
Sure. So the Wi-Fi dataset uses something called channel state information, or CSI, and this basically captures how Wi-Fi signals propagate through the environment. So, when a Wi-Fi signal bounces off of an object, it changes the amplitude and phase of the signal, and CSI can capture those changes.
Okay, so it's not just about the strength of the signal, but it's also about how it's been distorted by the environment.
Right, exactly. And then the UWB dataset, it uses time sequences of the reflected radar signals. So it's basically sending out these pulses of radio waves and then measuring how long it takes for those pulses to bounce back.
Right.
And because it's ultra-wideband, it has a very high bandwidth, which means that it can provide very fine-grained temporal resolution.
So it can see things changing really quickly.
Right. And then finally, the UMM dataset, it uses something called point clouds. So it's basically sending out these beams of millimeter wave radiation and then measuring where those beams reflect off of objects in the environment.
Okay, kind of like a radar system.
Exactly. And so you end up with this 3D point cloud that represents the shape of the objects in the scene.
Okay, so 3 very different ways of using RF to kind of see the world, but all of them can be used for pose estimation.
Right.
And I guess that's one of the points of this paper, is that they're trying to come up with a method that can work across all these different modalities.
Right, yeah, and they evaluated their approach on all 3 of these data sets.
Okay, cool. So they've got their method, they've got their data sets. How do they actually split the data up? Because I imagine that's important for testing generalization.
Yeah, so they actually used 3 different data splitting strategies. So first they did a random split, which is just, you take all the data, you shuffle it up, and you randomly split it into a training set and a test set.
Okay, standard stuff.
Yeah, but this isn't really a good test of generalization because the training and test sets are drawn from the same distribution.
Right, so the model could just be memorizing patterns in the data and not really learning to generalize.
Exactly. So they also did 2 other splits that are more challenging. So they did a cross-subject split where they trained the model on some subjects and then tested it on different subjects.
Okay.
And then they did a cross-environment split where they trained the model in one environment and tested it in a different environment.
Okay, so those are the really tough tests, right? Because that's where you're really trying to see if the model can handle those domain shifts that we were talking about earlier.
Right, exactly.
Okay, so they trained their model, they evaluated it on these different splits. What did they compare it to? What were the baseline methods that they were using?
So they compared their approach to a number of state-of-the-art methods for RF-based pose estimation.
Okay.
And they basically chose representative methods for each of the RF modalities that they were looking at.
Okay.
So for the Wi-Fi and UWB datasets, they compared to methods like WiPose, WPNet, WPFormer, and PyW3D.
Okay.
And for the online wave dataset, they compared to methods like point transformer, poseformer, diffpose, and memdiff. So these are all methods that have been published in recent years, and they're considered to be pretty good at what they do.
Okay, so they're really trying to compare against the best of the best here.
Right.
Okay, and then for actually measuring performance, what kind of metrics did they use?
So they used standard metrics for evaluating 3D human pose estimation. So the main one is MPJPE, which stands for mean per joint position error. And this basically measures the average distance between the predicted joint locations and the ground truth joint locations.
Okay, so lower is better.
Right, exactly. And then they also used PA-MPJPE, which stands for Procrustes Aligned MPJPE, and this is a variant of MPJPE that takes into account the overall scale and orientation of the pose.
Okay.
So it's basically trying to align the predicted pose with the ground truth pose before calculating the error.
Okay.
And then finally, they also use MPJDLE, which stands for mean per joint distance on limbs error. And this specifically measures the error on the limbs, which is often more important than the error on the joints themselves for many applications.
Right.
Like if you're interested in, tracking someone's gait or their movements, you care more about how accurately you're predicting the position of their limbs than the position of their individual joints.
Okay, so they've got these 3 different metrics. They've got their baseline methods. They've got their data splits. Let's get to the good stuff. What were the results?
Okay, so the results were pretty impressive. They found that GenHPE consistently outperformed the baseline methods across all 3 data sets and all 3 data splits.
Okay.
And the improvements were particularly significant in the cross-subject and cross-environment settings, which is where generalization is really important.
Okay, so it really seems like this approach is doing something to address that issue of domain shift.
Yeah, it definitely seems that way. So for example, on the Wi-Fi dataset in the cross-subject setting, GenHPE achieved an MPJPE of 42.6 millimeters, which was 52.2 millimeters lower than the best baseline method, which was PyW3D.
Okay, so that's a huge improvement.
Yeah, that's a really big difference. And then in the cross-environment setting on the same dataset, GenHPE achieved an MPJPE of 55.1 millimeters, which was 10.6 millimeters lower than the best baseline method.
Still a big improvement.
Yeah, not as big as the cross-subject case, but still very significant.
Okay, so what about the other data sets? Like, did they see similar improvements on UWB and MLM wave?
They did. So on the UWB dataset, the improvements were a little bit smaller, but still significant.
Okay.
So in the cross-subject setting, GenHPE achieved an MPJPE of 57.3 millimeters, which was 14.9 millimeters lower than the best baseline method. And in the cross-environment setting, it achieved an MPJPE of 64.2 millimeters, which was 6.9 millimeters lower than the best baseline method.
Boy.
And then on the image HPE, the improvements were even smaller, but they were still there. So in the cross-subject setting, GenHPE achieved an MPJPE of 78.2 millimeters, which was 5.3 millimeters lower than the best baseline method. And in the cross-environment setting, it achieved an MPJPE of 84.1 millimeters, which was 3.1 millimeters lower than the best baseline method.
Okay, so it seems like the amount of improvement that they get from this approach kind of varies depending on the RF modality that they're using?
Right, and they actually hypothesize that this is because the different RF modalities are affected by different types of confounders.
Okay, that makes sense.
So for example, Wi-Fi and UWB signals are more affected by environmental factors like multipath propagation, which is when the signal bounces off of multiple surfaces in the environment.
Okay.
Whereas an M-wave signals are more affected by factors like the material properties of the objects in the scene. So they suggest that their approach might be more effective at mitigating the types of confounders that affect Wi-Fi and UWB signals.
Okay, that seems reasonable. And it's worth noting that even though those improvements on the M-wave dataset were smaller, they were still statistically significant.
Right.
So it's not like their method was doing nothing. It was still making a difference.
Exactly.
Okay, cool. So they did all these experiments. They show that their method works really well compared to other methods. But in machine learning, it's always important to kind of understand why it works, right? Like what are the key components of the method that are actually driving those performance gains?
Right, and that's where the ablation study comes in.
Right.
So an ablation study is basically where you remove different components of your method and you see how that affects the performance.
Yeah, so you're kind of like taking the engine apart piece by piece and seeing which parts are really essential.
Exactly. And so they did a bunch of ablation experiments to try to understand what parts of GenHPE were really important. So first, they looked at the different generative models that they used. Remember, they experimented with DDPM, DDIM, and CJAN.
Right.
And they found that all 3 models actually performed pretty similarly.
Okay.
Which suggests that the specific choice of generative model is not that critical to the success of their approach.
Okay.
As long as you're using a generative model that can learn the relationship between pose and RF signals,
Yeah.
you're going to get some benefit.
All right.
But they did note that DDIM was a little bit more computationally efficient than DDPM.
Yeah.
So if you're concerned about, runtime or memory usage, DDIM might be a good choice.
Okay. Good to know.
And then they also looked at the effect of removing the skeleton embedding. So remember, they used a skeleton embedding to represent the pose in a way that captures the relationships between different body parts.
Right.
And they found that if they remove the skeleton embedding and they just use the raw 3D joint coordinates as input to the generative model, the performance dropped significantly.
Okay. So that skeleton embedding is really important.
Yeah, it seems to be playing a key role in helping the model learn the relationship between pose and RF signals.
Okay.
And then finally, and probably most importantly, they looked at the effect of removing the generative counterfactual component altogether.
Okay, so this is like the heart of their approach, right? The whole idea of generating these alternative realities where body parts are missing and using that to tease apart the signal.
Yeah.
So what happened when they removed that?
So when they removed the generative counterfactual component, the performance absolutely tanked. Like it was much, much worse than any of the baseline methods.
Wow. Okay, so that really shows that this is the key ingredient that's making their method work.
Yeah, it really highlights the importance of that component.
Okay.
And actually, they even tried just using the decoder without the encoder. So, just feeding the domain-independent representation directly into the decoder, and that performed even worse than removing the generative counterfactual component.
Wow. Okay, so it's not just that they're creating these great features, it's that they're using those features to train a better encoder.
Right.
And that encoder is really learning something important from those features that it wouldn't be able to learn otherwise.
Yeah, exactly. I think that's a really key takeaway from this ablation study.
So overall, it seems like this GenHPE approach is a pretty big step forward in RF-based pose estimation.
Absolutely, yeah.
Like it's really addressing this key problem of generalization, which has been plaguing the field for a while.
Yeah, and I think the clever use of generative counterfactuals is really what makes this approach stand out.
Yeah, it's a really cool idea. It's like they're using AI to kind of do thought experiments about what the world would be like if things were different, and then using that to learn something about the real world.
Yeah, I like that way of putting it.
All right, so we've talked about the problem, we've talked about their solution, we've talked about the experiments, but now I want to get to the really fun part, which is our novel notions segment.
Right.
So this is where we put on our speculative hats and we think about, what are some exciting directions that future research could take based on this work.
Yeah.
So, reading this paper got me thinking about all sorts of things. And I'm curious to hear your thoughts on this. But one thing that I was particularly interested in was this idea of personalized pose estimation.
Personalized pose estimation, yeah.
So, imagine a scenario where you're using RF-based pose estimation to do health monitoring in the home.
Okay, yeah.
So, you have an elderly person living alone, and you want to be able to crack their movements and make sure that they're okay.
Right.
And, one of the challenges there is that each person is different.
Right.
Right. And we talked about this earlier with the confounders, but in this case, it's not just about like the size and shape of their body. It's also about like their specific movements, their gait, the way they walk.
Right. And even how those things might change over time.
Exactly. So maybe they have an injury or they start to develop some kind of mobility issue.
Right.
And that's going to change the way that their body interacts with the RF signals.
Right.
So my thought was, what if we could take this idea of generative counterfactuals and kind of personalize it?
Personalized counterfactuals.
Yeah. So instead of having like one generative model that's trained on a bunch of different people, what if we could have a generative model that's specific to each individual?
Okay. I see where you're going with this.
So, maybe you have this initial calibration phase where you collect some data from the person and you train a generative model that's specific to them. And then you use that model to generate the counterfactuals. And then you can use that to train a pose estimation model that's really tailored to that individual.
Right. And I think that's a really interesting idea because it gets around this problem of having to like train a model on a huge data set of people and then hoping that it will generalize to this specific individual.
Right, yeah.
Instead, you're really focusing on learning the specifics of that person's movements and how those movements are reflected in the RF signals.
Yeah, and I think that could potentially lead to much more accurate and robust pose estimation, especially if you're tracking someone over a long period of time.
Right, and especially as those movement patterns change over time.
Exactly. So that's one idea, and I think there's a lot of interesting research that can be done in that area. Like, how do you efficiently train these personalized models? How do you adapt them as the person's movements change?
Right.
There's a lot of cool questions there.
Yeah, absolutely.
What other ideas did you have?
Okay, so another idea that this paper got me thinking about was, what if we could use counterfactuals not just with RF signals, but with other sensing modalities as well?
Okay, so like multimodal counterfactuals.
Yeah, exactly.
Interesting.
So, imagine a scenario where you have RF sensors and you also have maybe some cameras or some inertial sensors or even some microphones that are picking up sound.
Okay.
And you're trying to fuse all of this information together to get a really accurate estimate of the person's pose.
Right.
And so, you could train a separate generative model for each of these sensing modalities, and then you could generate counterfactuals for each of them.
Okay, so you're saying, like, you remove the person's arm in the RF signal, and you also remove the person's arm in the camera image, and you also remove the person's arm in the inertial sensor data.
Oh, exactly.
And then you see how all those different signals change.
Right. And the interesting thing is that by looking at how those signals change across different modalities, you might be able to learn something about how those modalities are related to each other.
Okay.
So, for example, you might learn that when the person's arm is missing in the RF signal, there's also a corresponding change in the sound that the microphones are picking up.
Oh, interesting.
Or maybe there's a corresponding change in the way the person is moving as measured by the inertial sensors.
Okay, so you're not just learning about the individual modalities, but you're also learning about the relationships between them.
Right. And I think that could be really powerful because it could allow you to, fill in the gaps if one modality is missing or if one modality is noisy.
Right.
So, if the RF signal is blocked by something, you might be able to use the other modalities to still get an accurate estimate of the pose.
That's a really cool idea. So It's like you're using the counterfactuals to kind of create a more complete picture of the person's movements, even if you don't have complete information from all the sensors.
Exactly.
That's really cool.
Yeah, and I think there's a lot of potential there for improving the robustness of pose estimation in challenging environments.
Right. And thinking about these personalized models and these multimodal models, I'm just thinking about all the different applications that this could be used for. Like, you mentioned health monitoring in the home, but you could also use this for sports analytics.
Right.
You could use it for, human-robot interaction.
Yeah.
Like there's so many different areas where this could be really useful.
Yeah, absolutely.
And I think the fact that this approach is so general and it can work across different types of RF signals just makes it even more promising.
Yeah, I think that's a key strength of this work.
All right, well, I think this has